In the last lecture, we looked at how we can increase the amount of water available to humans by tapping into new water sources, either building dams to trap new water in an area, or drilling down to make groundwater available for use, or moving water from one watershed to another watershed using a water diversion project. What we're going to talk about for the first part of this lecture is how do we get more water by just using the water that we already have more efficiently. So the first way we're going to talk about is we're going to talk about conservation, utilizing less water to do the same jobs. Then we'll go on and we'll talk about technological solutions, how to make dirty water available as clean water once more. As a nation becomes more developed, its water use increases. Individuals start living in homes, and those homes have gardens around them, so the number of lawns increases, therefore the outside of the home is taking up more watering. Inside the house they tend to have dishwashers and washing machines, flush toilets, showers, internal plumbing running their baths, so all of these items are taking more and more water. So as we move through the demographic transition, we see that water use is increasing per person. Now most of that water is not used for drinking and cooking. Most water is used just as a solvent to carry away wastes. So when we look at the next slide, we can see that washing the dishes, carrying away food particles, carrying away wastes as urine and feces, washing soil off of our body and hair or out of our clothes is what we use most of the water in our areas for. So just as a solvent to carry away waste, we're not actually using up that water, we're just removing the water from the hydrologic cycle, adding pollutants to it, and then passing it back out into the environment. So if we can be more efficient in the way that we utilize that water, that means there's lots more water available for other people to use. Now there's that section there, the 29% is used for water in the garden, so if we could water our plants more efficiently, we would also have much more water available for other people to use. So we'll look at a few ways we can use water more efficiently inside the home, and then I'm going to let you look at ways that you can use water outside the home more efficiently. The first thing we can say is countries that pay more for their water are much more efficient with how they use water than countries that don't pay a lot. There is an attitude that says that water is a right for all people and therefore should be free. I know this debate raged in the United Kingdom when I lived there, how much should people pay for water? But there is no deniability that if it costs more, people are much more careful with it. From the graph we can see that Germany charges much more per unit water than the United States does. So if you're paying a water bill in the United States and it's costing you about $30 a month, that same water bill in Germany would be costing you just a little over $60 a month because the water is just more expensive. Now if you look at the brown bars, you can see that because of the cost of water, Germans are much more careful with how they use their water and therefore conserve more water per month, so their bill actually comes out to be slightly less than yours because they're using less water. So one simple way of making people more efficient at using the water they have is to just charge them more for it. People will then modify their behaviors and find ways to use less water. Politicians that just raise the price of water, though, are likely to be out of a job come next election cycle. So we really need to educate our population on how to conserve water so that any increase in cost does not actually reflect an increase in bill. As the price goes up, the usage should go down so that our cost remains round about the same. So how can we actually save water inside the home? Well, most of these are pretty just intuitive. If you compare washing in a shower to washing in a full tub, washing in the shower is going to take much less water. So showering, as long as you're not in there for 20 minutes, is much more efficient. Toilets with more efficient designs also can use much less water per flush. There's a difference between how much power it takes to flush a toilet that has feces in it compared to a toilet that only has urine in it. So we have double flush type toilets in Europe, where if you hold the button down just for a short amount of time, you get one type of flush, just enough to take away liquid waste. And if there's solid waste in there, you hold the button down and hold it in place, and that will give a different style of flush that's much more forceful to flush away the solid waste. So just designing toilets to utilize less water is a way to easily conserve water within our municipality. Now, of course, there's also things like running your dishwasher only when it's full, running your washing machine only when it's full. Washing machines and dishwashers are the most efficient when they have a full basket. If you don't fill the basket completely, then you're using more water than you should be to do that amount of laundry or that number of dirty dishes. Also, washing machines that are front loading utilize much less water than top loading washing machines. So just changing how your washing machine looks to utilize less water will also save you money on your water bill, as it will save you money on your electricity bill. Having less water means there's less water to heat up to make that wash the temperature that you need it to be, so they use less electricity as well as less water. And that leads nicely into this idea of just being more energy efficient. Utilizing energy actually causes the use of water, because our power plants have to use water for cooling, and that cooling water is evaporated off into the sky. You see the big steam coming out of the cooling towers, and therefore that water is not available as drinking water or washing water to your local town. So if we can be more energy efficient or switch to energy sources that don't use as much water, we can actually conserve water and have more water available for our municipalities. So wind power, for example, doesn't take up anywhere near the amount of water that a coal plant would to make the same amount of energy. And last but not least is the leaks. Most water pipes have been in the ground for quite a long time. So most municipalities leak water as it goes from their water towers to your house. So a priority should be replacing old water pipes. If we can replace old water pipes, then we will deliver much higher quality water to individuals' homes and lose much less water as it goes from the water treatment plant to the place where it's going to be used. This would allow us to actually withdraw less water from the river each week, and therefore allow more water to be used by towns downstream. Now notice that I did not go over any methods for actually using less water outside in an agricultural or garden setting. So one thing you are going to have to look up is ways that you can more efficiently water plants in an agricultural setting. How can we deliver water to the plants more efficiently rather than just to the ground around the plants? And do the same thing for your home. And the last part of this lecture is how do we implement technological changes to produce clean water from water that would not normally be drinkable. And we're going to do this in two steps. First of all, we're going to look at using salt water to make drinking water, and then we're going to look up cleaning dirty water to make drinking water. Right. So let's start out with how do we turn salt water, ocean water, into drinking water? And that process is called desalination. Desalination is the removal of salt from salt water so it becomes fresh water suitable for drinking. One of the most common ways of doing desalination is called reverse osmosis. Now in reverse osmosis there is a thick filter membrane, and this filter membrane will not let salt ions pass through the membrane, but will let water molecules pass through the membrane. So seawater is pumped out of the ocean and then pressurized, and that pressure forces the water molecules through the membrane, generating a stream of pure water. The salt particles are trapped within the membrane and produce what's called the brine discharge. So this brine is highly salt concentrated water. So it's water with lots and lots of salt in it. Now, there's no doubt that reverse osmosis desalination makes extremely pure drinking water. It's a great way of doing it, but it does have some downsides. And the major downsides are this. Number one, it costs a lot. Unlike just collecting rainwater like a reservoir does, this takes large amounts of electricity to actually run the pumps and run the osmosis engines. So it's much more expensive than just collecting water from your local river. The second downside is you produce this really high salt concentration brine. Where are you going to put it? No matter where you put that highly salt concentrated brine, it's going to cause a pollution problem. Even if you put it back into the ocean, the end of the pipe where it goes back in is going to have much higher salinity than normal seawater, and those high salinities will kill any fish or invertebrates that go into it. So it is going to have an impact. If you put it on the land, it will definitely kill any plants or animals that are in that area. So when you're doing reverse osmosis, you have to understand that it is going to have an impact on the environment around the plant. So again, this is an example of you can never do just one thing. You can't just suck salt water out of the ocean and turn it into fresh water and expect it all to be positive. As soon as we do that, we get some negative impacts as well. This idea that the brine discharge is going to impact negatively the environment somewhere. During municipal water use, add in pollution to the water cycle. And we've already said that most of the water is used just as a solvent to wash away dirt and grime, feces and urine. Now there are many different types of pollution that are listed in your textbook, from thermal pollution through chemical pollution, and we're going to focus mainly on sewage pollution. So you got to know that the solution to pollution is not dilution. This was a saying first brought out in the 1970s. The solution to pollution is not dilution. And what that's really saying is, if you take a chemical and put it into the environment and let a river wash it away, it hasn't really gone away. The hydrologic cycle means that we have a cycle. It may be carried from one place to another, but that chemical is still present. If you want to get rid of the chemical, then get rid of the chemical. Don't just let it be washed downstream for somebody else to deal with. So with all of the waste that we're producing in our urban areas, from our washing machines and our dishwashers, our toilets and our showers, the natural environment can just not cope with that amount of waste being delivered in such a short time. With a city the size of Atlanta, there's just too much waste flowing into the natural waterways for natural processes to degrade it. When we combine this idea that the natural environment just physically cannot break down the pollution quick enough with the fact that more than 36 states expect a water crisis in the next 10 years, where they're water stressed, their population is growing faster than their water supply, we have the ability to kill two birds with one stone. How can we clean up our wastes and produce usable water? The Clean Water Act protects waterways by regulating pollutant discharge in two separate ways. First, it sets water quality standards for the surface waters. They're the lakes and the rivers. It says that only X amount of this chemical can be present in this water. And two, it sets a limiting amount for discharges into the water from individual businesses and areas. So it's going to say that the city of Milledgeville, right here where GMC is, can only put so much sewage into a waterway. And it's not actually the sewage it's talking about an item called BOD, which is biochemical or biological oxygen demand. So our Clean Water Act is going to limit how much of a pollutant can be actually released into a waterway. Now, when we're trying to measure what that pollutant is, the Clean Water Act will actually tell us these are the specific criterion pollutants that are listed. And I'm not going to go through and do all of them because there's just physically too many chemicals listed. But the one we'll talk about the most is this idea of BOD, biochemical oxygen demand, sometimes called biological oxygen demand. So BOD is the amount of oxygen required to decay a certain amount of organic matter. It's how much oxygen is used up by that water as the bacteria grow in it because of the waste that's in the water. If we add too much organic matter, feces or urine, to a water body, then the bacteria grow too fast and they use all the oxygen up. Once it has no oxygen in it, the water is said to be anaerobic. Now obviously fish can't live in anaerobic, no oxygen conditions, so that will kill fish in a waterway. But it also allows the growth of anaerobic bacteria, bacteria that don't need oxygen to survive. These bacteria grow, break down the waste, produce nasty stinking odors and awful tastes, and make the water unusable in terms of drinking water. So we can't allow too much waste that would increase BOD to flow into a river. We can't allow the BOD of the river to rise too much. So rather than put the waste in the river and have it be decayed by bacteria there, we need to contain the waste and deliberately use bacteria to break that waste down. Not only does sewage contain a bunch of chemicals that are going to be broken down using oxygen, sewage also contains disease-causing organisms or pathogens. Waterborne pathogens are one of the worst problems facing the human population in less developed countries every day. Sewage treatment plants, therefore, must make sure that they remove these disease-causing organisms before they release water back into the environment. And sewage and bath and washing machine runoff also contains plant nutrients. Now these plant nutrients, nitrogen and phosphorus, are what is also found in fertilizer. So if we add these nutrients to the water, we are fertilizing the water. Now that may seem strange to be listed as a problem. Some people would think, well, having fertilizer added must be a good thing. The problem is if we add too much fertilizer. Adding too much fertilizer produces excessive growth of algae. And this excessive algal growth is called eutrophication. So eutrophication would occur and we have this bright green pea soup-like look to our waterway. Now eutrophication is bad because of two reasons. Number one, all the algae in the water block out the sunlight from reaching the aquatic plants at the bottom of that water body, and therefore it kills off all of the aquatic plants. And number two, when those plants die and when the algae die, they become an organic waste that has to be broken down, and they're broken down by bacteria. The bacteria use up oxygen, and therefore they increase BOD, they increase the biochemical oxygen demand. That is, when you do eutrophication, the amount of oxygen in that water will be decreased. If the amount of oxygen drops too much, you're going to kill all of the animals that live in that water. Now all of the different types of pollution that flow into water can be broadly divided up into two categories. Point source pollution comes from an area that you can point to, comes from a factory, comes from a pipe, comes from a farm, and you can go, this is where the pollution is coming from. You can point to where that pollution is coming from. Now that is easily dealt with because you can write legislation to prevent that pollution continuing. You can write laws so that you can fine people that are producing that type of pollution and therefore make it stop. Non-point source pollution comes from wide areas, comes not from a single farm but from an entire hillside, comes not from a single factory but just appears to be in the air. So non-point solution is very difficult to deal with. If you can't point to where the solution is coming from specifically, who do you know who to fine? How do you write a law to stop it from occurring? So non-point solution, because they're more diffuse, more spread out, it's not one single place, not one single point, are very, very difficult to legislate against, are very difficult to take enforcement action against, and therefore are very difficult to stop. So if that's all the stuff that's in sewage and in the water that flows away from our homes towards the sewage treatment plant, how are we going to clean it up? Now, sewage treatment plants basically have 5 steps to their working. The first step is primary treatment. Now, just remember that there are some videos out on the website for these sewage treatment steps, so make sure you watch them so you've got an idea of how the sewage treatment plant does work. Primary treatment is separating solids and liquids. So primary treatment is going to involve a series of bar screens that separate out all the trash and junk that gets flushed down sinks, that gets washed into our gutters. So if you've put potato peel in down the sink, or you've flushed a tampon or flushed a condom, then it's going to remove that from the sewage right at the beginning. Right after that, the sewage is going to go into a big holding chamber. It looks just like a very large swimming pool, and it's just going to sit there. And this will allow the solid parts of the sewage to sink down to the bottom of the tank and be separated out from the liquids. It also is going to allow fats and oils to float to the surface and be scraped off. So what would be left with is just a liquid waste. And this liquid waste would be called the primary effluent. Effluent being the liquid portion. So primary treatment is going to separate solids from liquids. It's going to leave us with a sludge, the solid portion, and primary effluent, the liquid portion. Secondary treatment is a biological breakdown of those wastes. So we've got to do this in 2 steps. 1, we've got to look at the liquid wastes, and then 2, we've got to look at the solid wastes. So let's start just with the liquids. So the effluent is going to flow into a series of filters, and those filters are going to use biological organisms to degrade the pollution that's in it. They're going to take the organic matter and they're going to break that organic matter down into just plant nutrients. So it could be a trickle-in filter with a bunch of plastic or stone particles over which the water flows. Or it could be an activated sludge system, which looks like a huge big bath that's got water and air pumped into it and just mixed up, so it looks like a big boiling sludge-filled pool. And all of those are just allowing microbial organisms to grow like crazy and use up all of the organic matter that's actually in the sewage that's being treated. Now at the end of that process, it goes into another holding tank, and that holding tank, it just sits there again, and the solids drop out of it. So we're converting the sewage into microbes, and those microbes are large enough that they can drop out of the water and be collected as sludge. So what we're left with is liquid that then would be called secondary effluent. So this is the second stage. It's the water that's left at the end of that. That's secondary effluent. And all of the sewage has been taken out of it, but what left in it is a bunch of plant food and a bunch of pathogens. Tertiary treatment is not done at every single plant in the nation. But tertiary treatment is basically the biological removal of nutrients or the removal of other chemicals that are in the sewage effluent. So this is a special treatment to remove special chemicals, either the plant nutrients or some other chemical that is polluting that effluent. So most tertiary treatment plants, if they're just removing plant nutrients, use plants to remove those plant nutrients. So it's going to look like a big old swimming pool with a bunch of plants growing in it, sucking out the plant nutrients. So a swamp could be used for the same thing, because swamps are natural tertiary treatment areas. They're natural biological nutrient removal areas. So that effluent, after being treated, then has to have all of the pathogens removed. It has to go through disinfection. So what's normally going to happen here is chlorine gas is going to be added to it, or bleach will be added to it. Both of these things will kill very efficiently any pathogens that are in the water. Now, sodium hypochlorite or bleach will just kill off the pathogens and can be left in the remaining effluent. If it's chlorine that's in there, chlorine is highly reactive and can't be left in the water before it's discharged, so they're then going to add some chemicals to remove the chlorine. And what's normally used is sulfur dioxide, just small amounts of sulfur dioxide that will react with that chlorine so that we don't have free chlorine being released. And finally, the effluent is then released, so put back into the ocean or put back into the river. Now, this pipe here where we've seen discharge has not gone through a very good set of sewage treatment. You can see that because it still looks like coffee coming out there. It's still nasty and dirty. But if we'd have done efficient primary, secondary and tertiary and then disinfection of that liquid, it should have looked just like basic tap water. It should have looked just like a tap water that's been flowing out of there. Now, because of that, when it flows into the river, it is water. So when it moves downstream, the next town can suck that water back out the river and utilize it as drinking water all over again with its drinking water clarification plant. So here we are recycling water, using water in one town, cleaning that water back up, put it back in the river so the next town can use it. That should go through the process of cleaning it and put it back in the water so the next town can use it. So that's all of the liquid side of it. What about the solid side? So the effluent portion of the waste was the liquid portion. That liquid portion was separated from the solids by primary treatment. It then went through secondary treatment when microbes digested it and used all of the waste that was in there as food to generate more microbes. Those microbes were then settled out, collected from the liquid, leaving just the water. Then, if it was at a tertiary treatment plant, it had the plant nutrients removed from it by tertiary treatment. And then the pathogens were removed from it by disinfection. So it was disinfected before being released back into the environment where people could utilize that water again. Now, what we haven't talked about is what about those solids? What about the solids that were separated out during the primary treatment, the sludge? And what about all the solids that were made, actually produced by secondary treatment? All of the bodies of those bacteria and microbes that we collected at the end of secondary treatment. What happens to that sludge? Now, all of that sludge together is fed into the sludge treatment. And at most sewage treatment plant, that's done an anaerobic sludge digester. Again, no oxygen. It's anaerobic. So this does not have any oxygen in there. And that's done because we want to break this sludge down. We want to degrade this sludge using special groups of microbes to generate biogas. And the biogas that we're actually going to make will be methane or methane. So the sludge is collected and pumped down pipes into an anaerobic digester. There it's heated up, it's warmed up, and bacteria are added, and the bacteria break that sludge down. They break the sludge down to types of alcohol, and then other bacteria break those types of alcohol down into methane. So bubbling up through the sludge, we get methane that can be collected. This methane is collected and can be used for a variety of purposes. One is it's often burnt in the boilers that actually heat the anaerobic digester. This thing needs to be running at about 95 degrees, so they burn the methane that's produced to actually generate the heat that works this sludge digester. If it's burned efficiently, it can also be used to make electricity. So you can make electricity that will actually mix turn the mixer to drive the sewage treatment plant. If it's burned efficiently, it can also run the lights and the computers and all the other equipment at the sewage treatment plant. And if it's a plant for a large city, it can even generate electricity for that city. Portland, Oregon has anaerobic digesters that generate large amounts of methane, and that methane goes into a fuel cell that produces electricity for homes within the city. So these anaerobic digesters digest down the sludge until it can no longer produce any methane. At that point, they're moved into a second digester where the sludge sits and is given time to digest even more. Once it's broken down some more, the sludge has to be removed. And there's really three fates that can happen to that sludge. Number one, it is taken, mixed with a polymer, so it comes out looking a bit like Play-Doh, and then is carried and put in a landfill. Now, putting sludge in landfill is extremely expensive. You have to pay for the polymer that makes it like this putty, so it doesn't just ooze out of the landfill and cause problems at the landfill. And you have to pay the tipping fee to actually take it to the landfill. So that's the most expensive thing to do with it. The second thing to do it is to land apply it. It comes out as a sludge, and in that sludge form it goes into a big tanker truck and is taken and sprayed onto land that is not going to be used for human consumption. So it's not going to be put on crops like cabbages or radishes. Instead, it's put on crops like silage fields or hay fields. And then the farmer is going to cut those down and feed them to cows. So he's getting a higher rate of return on his farmland, and at the same time getting rid of the waste product from the sewage treatment plant. And the last thing that can happen to it is that it's just put in drying beds, and these are like very, very small, and by small I mean thin pools out around the sewage treatment plant. So around about 3 inches of sludge is put into each pool, and there it's just left to dry in the sun. And when it dries to a brown potting soil like consistency, and then that can be applied as a fertilizer. Now the key thing there is it's put very thin, because this sludge can still contain pathogens, and you need to destroy the pathogens before it can go into contact with any human. So a great way of destroying pathogens is sunlight. So by putting it in these very thin drying beds, it exposes it to large amounts of sunlight, to ultraviolet light, while it's drying up, and will render it usable. If you have to use it without a drying bed, then you're going to have to disinfect the sludge as well, using some type of gas like chlorine, or utilizing electric ultraviolet light. So metropolitan areas must plan how they're going to use water, and they have to deal with 3 basic things. Number one, they've got to supply water for human and industrial needs. So they have to plan for the amount of population growth that they have and supply enough water for all of those humans, whether it be through building dams or tapping into the groundwater or utilizing desalination plants. They have to understand that once those humans have used that water, most of it is just going to be flushed around our sewage system. So most of that water is just going to be flushed right back down our drains and needs to be cleaned up. So they have to have a wastewater collection system and sewage system that can remove the pollutants from that water and make that water available to the next group of humans. And the third thing they have to do is they have to deal with stormwater. Now, if you remember at the beginning, we said that humans have decreased the amount of infiltration and increased the amount of runoff that occurs in our hydrologic cycle. So when we have our cities, they have large amounts of runoff. And what are we going to do with that stormwater? The problem with all that runoff is that it quickly goes into our rivers without that infiltration period and causes flooding. Not only does it cause flooding, as it floods over our parking lots and over our gardens, it carries with it large amounts of pollutants, oil that's dripped on the parking lot, fertilizers that we've sprayed on our lawn. So we have to manage what's going to happen with the stormwater. Very few municipalities have stormwater flow into their normal sewer system that will go to the sewage treatment plant. And the reason for this is quite simple. If you have a huge downpour, a tropical storm that lands in your area and it rains and rains heavily, that rainwater entering your sewers may in fact fill your sewers, and therefore you would have raw sewage overflowing. And municipalities don't want this, so they're going to have separate storm sewers from their sanitary sewers. If you just do that though, then that stormwater will flow down your stormwater sewers into the local river and dump all of its pollutants into your local river. And the Water Quality Act of 1987 says that you can't just take all of your stormwater and dump it into your river, because you're producing a non-point source pollution. Every single car in your municipality is leaking some oil. All of that will be funneled directly into the local river. So they're going to have to clean it somehow. And how do you do that without costing an arm and a leg and pushing up your tax burden? And really, the simplest way is to utilize swamplands. Swamps are natural tertiary sewage treatment areas. They remove chemicals and plant nutrients from water. Swamps also act as large sponges that allow infiltration to occur. So in terms of artificial swamp areas, it's a win-win situation for a municipality. Not only does the swamp improve the water quality of that water that ends up in the river, it also increases the amount of infiltration and therefore increases the groundwater available to the municipality. And third, it decreases the likelihood of downstream flooding, because the swamp can act like a big sponge and soak up large amounts of water. It mitigates this peak and trough idea of water flowing quickly when it rains into the river and then there being no water left to fill the river during dry times. So as you read the book, you should notice that artificial swamps are an excellent way of dealing with stormwater runoff.